Hello, my name is Muhammad Fakrul Haziq bin Muhammad Fauzi. My student ID is 2024913039. For introduction about electric vehicle is electric vehicle are vehicle that use electric motors and electric stored in battery to move instead of using petrol or diesel fuel. What are electric vehicle? Electric vehicle nowadays use battery technology, fast charging system and growing concern for the environment. Modern EVs are becoming more efficient, affordable and play a key role in promoting sustainable transportation for the future. For modern importance, electric vehicles are important in modern time because they reduce air pollution, save energy and help protect the environment by lowering carbon emission. For the historical about EVs is electric car have exist since the late 1800s, but they decline in popularity after petrol car become cheaper and more powerful than a EV car, and they have become popular again in modern time due to the environmental concern and advance in battery technology.
So now I will explain the scientific principle of EV transportation. Now, electric vehicle or EV is an automobile that are operating based on the principle of electrochemistry and electromagnetism. Now, this principle is converting the chemical energy that has been stored into electrical energy and will activate the automobile mechanism. So, for example, there is a BEV car and also EV motorcycles. For the BEV car, this consists of five main components, which is the electric motor, the inverter, battery, control module, and a drivetrain. For the working principle of the BEV car, first, the power that has been stored will convert from the DC battery to AC for the electric motor. And when we hit the accelerator pedal, it will send a signal to the controller that adjusts the vehicle speed by changing the frequency of the AC power from the inverter to the motor. When the motor receives the AC power, it will connect and turn the wheels through a cord. When the brake are being pressed or the car is decelerating, the motor will become an alternator and produce power, and it will send back to the battery. Now, for the EV motorcycle, it consists of three main components, which is the rechargeable battery, electric motor, and a braking system. For the working principle of EV motorcycle, so EV motorcycle consists of two main components, which is the battery and also the motor. Now, the battery store the energy and was measured by kilowatt hours. So, the kilowatt hours, if it is higher, it means that the motorcycle will travel farther before it needs to charge again. Now, the motor will convert the energy in the battery into a mechanical motion. EV motorcycle also has a cooling system which was used to maintain the heat of the motor and also to prevent it from overheating. The controller, it will act as a medium of the motorcycle motion. When the throttle was squeezed, the controller decides the electrical current flow outputs from the battery to the motor. Now, if this current was more flows into the motor, the faster it will spins.
First, I will talk about electric vehicles, which are one of the most important current technologies in the automotive industry today. Electric vehicles use electric motors powered by rechargeable batteries instead of internal combustion engines that rely on petrol or diesel. One major advantage of this current technology is that it helps reduce air pollution and greenhouse gas emission. Electric vehicles also produce less noise compared to traditional vehicles, making cities quieter and more comfortable. In terms of real-world application, electric vehicles such as Tesla, BYD, Nissan Leaf, and Proton e-Mars are already being used by the public. In Malaysia, charging stations are being installed at shopping malls, highway, and residential areas. These real-world applications show how current technologies support the transition toward cleaner and more sustainable transportation. Moving on, another important development is hybrid vehicle technology. The current technology used in hybrid vehicles combines an electric motor with a petrol engine to improve efficiency. At low speeds, such as during traffic congestion or city driving, the electric motor is mainly used. When higher speeds or more power are required, the petrol engine supports the system. These combinations allow hybrids to reduce fuel consumption without sacrificing driving range. Looking at real-world applications, vehicles like Toyota Prius and Honda Insight are well-known examples of hybrid technology in everyday use. These cars are especially practical for drivers who want better fuel efficiency but are not yet ready to fully switch to electric vehicles. Another important current technology is regenerative braking. Normally, braking wastes energy as a hit. However, with regenerative braking, the system captures some of that energy and converts it back into electrical energy, which is then stored in the battery. This helps extend driving range and improve overall efficiency without changing how the drivers control the vehicle. In real-world applications, regenerative braking is widely used in electric cars, hybrid vehicles, and electric trains. Many drivers may not even realize it's happening, but it plays a big role in energy conservation. Beyond road vehicles, rail transportation has also benefited from advanced technologies. One example is maglev or magnetic levitation trains. This current technology uses powerful electromagnets to lift the train slightly above the track, removing physical contact between the train and the rail. With friction greatly reduced, maglev trains can travel at extremely high speeds while maintaining stability and comfort. A well-known real-world application of this technology is the Shanghai maglev train in China, which can reach speeds of over 430 kilometers per hour. This system shows how advanced rail technology can support future high-speed transportation while reducing mechanical wear and maintenance needs. Another important innovation is electromagnetic braking system. This current technology relies on electromagnetic force instead of mechanical friction to slow down vehicles. When the system is activated, eddy currents are generated in metal components, producing opposing magnetic fields that reduce speed safely and smoothly. This method is especially useful for vehicles operating at high speed or carrying heavy loads. In terms of real-world application, electromagnetic braking systems are used in high-speed trains, heavy vehicles such as lorry, elevators, and roller coasters. This system improves safety and reliability by reducing wear on mechanical brake components. Finally, Wireless electric vehicle charging represents an emerging current technology in the automotive industry. This system uses electromagnetic induction to transfer power wirelessly from a charging pad on the ground to a receiver in the vehicle. As a result, drivers can change their vehicle without physically connecting a cable, making the process more convenient and user-friendly. Although still under development, real-world application of wireless charging already exists in experimental EV charging stations and parking-based charging systems. Companies such as BMW and Virtuosity are actively testing and improving this technology to support wider adoption in the future. To conclude, these current technologies and real-world applications clearly demonstrate how the transportation and automotive industry is moving toward cleaner, more efficient and more advanced systems. This technology not only improve vehicle performance today, but also play a crucial role in shaping the future of global transportation.
Hi, so today I will talk about the benefits of using an electrical transportation. Let's start with the technical sides, which is energy efficiency. To really understand why this is a breakthrough, we have to look at how wasteful traditional gas engines are. When you put fuel in a normal car, only about 20% of the energy actually moves the wheel. The other 80% is lost as heat and friction. That is incredibly inefficient. Electric motors, however, are a masterclass in efficiency. They convert over 85% of the electricity from the battery directly into power. But the real magic happens when you step on the brakes. In a traditional vehicle, braking just creates heat and wears down your brake pads. But using a regenerative braking in electrical system, the motors act like a generator. It captures the momentum of the moving vehicles and turns it back into electricity, pumping it back into the battery. This means in stop-and-go city traffic, where a gas car at its worst, an electric vehicle as its most efficient. Moving on, let's talk about a major global shift, which is reduced dependence on fossil fuels. For over a century, our transportation has been trapped by oil. If there is a crisis in the Middle East or a trade war, gas prices spike and everyone will suffer. By switching to electric, we are finally decoupling our ability to move from the price of a barrel of oil. Electricity is a flexible fuel. We can generate it using local domestic sources like solar, wind, hydro, or even nuclear power. This provides a massive boost to national energy security. Instead of spending billions to import oil from across the world, a country can produce its own fuel right at home. Furthermore, as the power grid gets greener every year, every electric bus or car already on the road automatically becomes cleaner without needing any mechanical upgrades. We are essentially future-proofing our entire transport network. Finally, we have a benefit that people often forget until they experience it: lower noise level. In our modern world, noise pollution is a serious health issue. Constant engine roar and vibration in cities contribute to high stress level and poor sleep for residents. Electric motors are nearly silent because they don't rely on internal explosions to move. When a city replaces its diesel bus fleet with electrical ones, the environment changes instantly. It's not just about the people outside, it's about the passenger experience too. Inside an electric train or bus, you can have a conversation at a normal volume, read a book, or relax in a quiet, vibration-free cabin. It makes public transit feel like a premium service. And while these vehicles are so quiet that they actually need fake safety sounds at low speeds to alert pedestrians, the overall result is a much calmer, more livable urban landscape. Let's moving on with the challenge that we have to face when we use electrical transportation. The first challenge we must address is often the most overlooked: technological adaptation. We often talk about the machines, but we forget that this transition requires a massive shift in human knowledge. For the last century, our entire global transport workforce has been built around the internal combustion engine. Now we are asking millions of people to essentially start over. Think about the mechanics and technician. A professional who has spent 30 years mastering pistons, transmission, and exhaust system now has to become an expert in high voltage circuitry, power electronics, and complex software systems. This is not just a small update to their skills, it is a completely different career path. We need massive nationwide retraining programs to bridge this skill gap. Furthermore, this adaptation extends to our first responders. Firefighters and emergency team have to learn entirely new safety protocols because electric vehicles fire behave differently and require different extinguishing methods than gas fires. From the factory floor to the local repair shop, the human side of the transition is a massive undertaking that takes significant time and dedication. Next, we have to talk about the engine of the electric world, battery technology limitation. While battery science is moving fast, we are still fighting against the law of physics in three specific areas: range, time, and lifespan. First, there is the issue of range anxiety. For long-haul shipping or heavy-duty train, today's battery often cannot match the incredible energy density of a diesel tank. Second, we have the refueling gap. You can fill a gas tank in 3 to 5 minutes, but even with the most advanced ultra-fast chargers, an electric vehicle can take 30 to 45 minutes to reach a functional charge. In the world of logistics, time is literally money, and this downtime is a major hurdle. Finally, we have to consider the life cycle. Just like the battery in your smartphone, EV batteries degrade over time and eventually need to be replaced, which is a massive expense. We also face the ethical and environmental challenge of mining materials like lithium and cobalt, and the future necessity of creating a massive global recycling system for the batteries once they reach their end of life. Finally, we have the most immediate barrier for any organization: high initial investment. Even though we know that electric vehicles save money on fuels and repair over time, the upfront cost is still a major shock to the system. Currently, an electric bus or a specialized electric train can cost twice, sometimes even 3 times, as much as a traditional diesel version. The reason for this premium price is primarily the cost of the battery technology and specialized electrical drivetrains. But the investment doesn't stop with the vehicle. A city or company also has to spend millions of dollars to completely retrofit their facilities. You can't just plug a fleet of buses into a standard wall outlet. You need specialized high voltage charging depots, which often require digging up streets to upgrade the local power grid. This creates a massive capital hurdle. Many smaller cities or businesses simply don't have the upfront cash to make the switch, making this financial barrier one of the biggest reasons the transition to electric isn't happening overnight.
Now we go to future development in EV transportation. Number 1, advanced battery technology. Future EVs will use solid-state batteries and improve lithium-ion batteries that offer higher energy density, faster charging, longer lifespan, and enhanced safety. This will significantly reduce charging time and increase driving range. Number 2, ultra-fast charging infrastructure. Expansion of fast and ultra-fast charging stations will allow EVs to charge within minutes rather than hours. Wireless charging routes and automatic charging systems are also expected to emerge. Number 3, lower cost and mass adoption. As battery production scales up and technology improves, EV price will continue to fall, making them affordable for a wider population. Government incentives and subsidies will further support adoption. Number 4, integration with renewable energy. EVs will increasingly be powered by renewable energy sources such as solar and wind. vehicle to grid V2G technology will allow EVs to store and supply electricity back to grid. Number 5. Autonomous and smart EVs. Future EVs will incorporate advanced autonomous driving features, AI-based navigation, and smart connectivity for safer and more efficient transportation. Number 6. Improves recycling and sustainability. Batteries recycling technologies will advance. Battery recycling technologies will advance, reducing environmental impact and dependency on rare raw materials, making EVs more sustainable. And lastly, expansion of EVs in public and commercial transport. Electric bus, trucks, delivery vehicles, and two-wheelers will become more common, reducing emissions in urban and industrial transportation. And lastly, we go to conclusion on EV transportation. Electric vehicle transportation represents a major shift towards sustainable and eco-friendly mobility. With continuous advancements in battery technology and charging infrastructure and renewable energy integration, EVs are becoming a practical alternative to conventional fossil fuel vehicles. Although challenges such as charging availability and initial costs remain, future innovations and supportive policies will accelerate EV adoption. Overall, EV transportations play a crucial role in reducing greenhouse gas emissions, improving air quality, and achieving a cleaner and more sustainable transportation system for the future.